8.3, geometric sequences and series. And yesterday was arithmetic. That was when you have a common difference between all the terms. You keep adding the same number every time. It might be adding a negative number, but you're adding the same number every time. Geometric is kind of like the grown-up version of that. And we're going to see that with a lot of these equations. Going from all those arithmetic sequence equations that I have on the chalkboard right now compared to the geometric ones we have today. And it starts off with the definition. A geometric sequence is a sequence in which there is a common ratio between each term. A common ratio. A common difference meant we were adding the same thing every time. A common ratio means we're multiplying by the same thing every time. You could be multiplying by a positive number or a negative number. You could be multiplying by an integer or a fraction, something bigger than 1, something less than 1. But if you multiply by the same number every time, that is a geometric sequence. Let's jump right into this first example. We have 3, 15, 75, 375, and 1875. I like arithmetic ones better because they're simpler, quite honestly. But sometimes we do have these geometric ones. So in this one, to get from 3 to 15, we added 12. 15 to 75, we added 60. 75 to 375, we added 300. So there's no way that this one is arithmetic because we keep adding different numbers. But we're in this section. It is, in fact, going to be geometric. On your calculators, I want you to check this. What is 1875 divided by 375? So you're taking one term, divide it by the one right in front of it. 1875 divided by 375. Then try 375 divided by 75. 5. And if we keep going down the line, what do you think 75 divided by 15 is? 5, and 15 divided by 3 is obviously 5. So we do have this common ratio. If I go from right to left, I divide them and I get 5. Or, more importantly, 3 times 5 is 15. 15 times 5 is 75. 75 times 3 is 75. And then times 5 again. We have this common ratio, and that common ratio is 5. Every term gets multiplied by 5 to give us the next term. That is the essence of a geometric sequence. Next one, 964, and then the fraction 8/3 and the fraction 16/9. Again, I know it's not arithmetic because from 9 to 6, I subtracted 3, then subtracted only 2, and then subtracted some fraction, so it's not arithmetic. However, if you took one term divided by the one in front of it, and then you tried it again, and you tried it again, and you tried it again, we should be getting the same ratio every time. Quick place to find this. What is 4 divided by 6? 2/3. And then 6 over 9 would also be 2/3. So our common ratio here is 2/3. That's how we can do a quick check. Take one term, divide by what's in front of it. That will give us our common ratio. Now for the formulas. First one, how do you write the explicit or direct, or sometimes called closed formula for a geometric sequence? It looks like this. Right above it, I'm going to write the formula for an arithmetic sequence. And I want you to notice how these are kind of like each other. They both have a sub 1, but in the arithmetic formula, we added. Instead, in the geometric, now we're going to multiply. So again, it's kind of like the slightly more difficult operation. Instead of adding, we're going to multiply. We have r for ratio instead of d, distance. And up here, it was distance times n minus 1. If we take that to a more difficult level, a more advanced level, instead of multiplying by it, we're going to raise it to the power of n minus 1. So those formulas are kind of simple or similar to each other. It's just that the geometric is just taking it in a more grown-up version. It's taking addition and making it multiplication. It's taking what was multiplication and it's making it become an exponent. So there is our first formula to find the a sub n in a geometric sequence. The next one we have is how do you find the common ratio? Well, to find the common difference, you would take one term and subtract the one in front of it. The other way we can talk about finding the common ratio is to use this. Now, these two gray are equivalent to each other. For the first gray one, if we know the two consecutive terms, we just divide them. That's what we were doing up here. But if the two terms aren't right next to each other, like if we know the third term and the 10th term, we'd have to do something like this. So it looks a little more complicated. Let's look at the common difference equation we had before. So if we want to find, if we know if it's an arithmetic sequence and we want to find the common difference, we subtract the actual terms and divide by n minus m. That's pretty similar to what we have here. For the arithmetic, we subtracted an minus am. The more grown-up version of that, the more difficult. Instead of subtracting, we divided them in here. They're both like working against each other. One is subtracting, the other one's dividing. And then instead of dividing by n minus m, we took that to more complicated and we said it is the root of n minus m. So again, very similar equations than what we had before. We're just taking them to slightly more advanced levels. So these are equations we're going to need to know as well as the arithmetic ones. The next one, and I need to confirm this with the other pre-calc teachers, is one that I believe will probably give you on the next quiz you have and probably the chapter test as well, because it's just a little bit more involved and there's not a great connection for this one. If we're trying to find the sum of a geometric series, this is what we would do. Take 1 minus the ratio to the nth power. How many terms are there? Divided by 1 minus r, and then multiply it by the first term. It's hard to compare this one to that sum formula for an arithmetic. It's like I don't see it like a nice similarity between them like I saw in all those other ones. So partly for that reason, partly because this one is kind of complicated. This is one I expect that we'll be giving you on the quiz. So I'm highlighting it now. We'll come back to it a little bit. Let's work on some examples. The directions: find a formula for the nth term. Find a sub n. And this first one, it is geometric. To find the common ratio, you could take 12 divided by 6, or 6 divided by 3, or 3 divided by 3/2. It doesn't matter which one you pick. What is the common ratio for this one? 2. 3/2 times 2, 3 times 2, 6 times 2. The common ratio is 2. So a sub n equals our formula for the nth term. Scroll back up here. I'm looking at this yellow equation. Is our first term times the common ratio of 2 to the n minus 1. That's it. Term 1, term 2, term 3, term 4. Quick check here. If I plug 4 in for n, 4 minus 1 is 3. 2 to the third power is 8. 8 times 3 is 24. Divided by 2 is 12. There's our output of 12. Just verified that it worked. So now what's good about this formula, if I want to know what is the 20th term, I'll just plug 20 in for n, run it through there, and I can figure out what that term is actually going to be. Next one. Slight variation. The first one, I listed out the first 4 terms, and then we just went with it. And this one, I'm telling you, this is a geometric sequence again. Otherwise, like it could have been arithmetic, it could have been something else even. I'm just telling you, it's a geometric sequence. And the goal is to find the formula for a sub n. Step 1, can you find the common ratio? We've got these formulas up here. Can you figure out how to use them? Calculator probably would be helpful for this one. So we're supposed to take 405 and divide it by 5. We're not subtracting, we are dividing 405 divided by 5. And then it says on the outside, take 7 minus 3. 7 minus 3 is 4. So we're supposed to take the fourth root of 405 divided by 5. I could put that in my calculator all in one step, or I could take 405 divided by 5 first, and I believe that's 81. And then I need to take the fourth root of 81. On my calculator, there's a couple of ways I can make that happen. One way, probably the most direct way, is to type in the number 4. I'll go to math, and then you'll notice that this fifth one down has an X just outside of that radical sign, so I'll choose that one. And it turns this 4 into the index number, so now it is the fourth root of 81, and that comes out to 3. So our ratio is equal to 3. What I know about this equation now is that a sub n is equal to whatever the first term is times 3 to the n minus 1. This is what I know for sure. The common ratio is 3. In other words, 3, 4, 5, 6, 7. The third term is 5. If I multiply that by 3, multiply that by 3, multiply that by 3, one more time, multiply it by 3 again, that should give us up to that seventh term of 405. That's what that 3 is really doing in this problem. What we don't have yet, though, is the first term. We need to plug in one of these values, and it doesn't really matter which one. A lot of times the smaller number is nice to use, so let's go ahead and try this one. Let's see if you can plug that in to this equation. So in this case, a sub 3 equals 5, n equals 3. So 5 equals a sub 1 times this 3 to the 3 minus 1, the second power, plugging 3 in for n. 3 squared is 9. Great. A times 9 equals 5. Divide both sides by 9. So a sub 1 equals 5 over 9. Final answer then, a sub n is equal to my first term times the ratio of 3 to the n minus 1. A little more involved problem. Arithmetic is nice and linear, common difference. The geometric, we have these common ratios, so we're doing more dividing, and we're doing these roots. That was all explicit or direct. Now we're going back to the other way you can write out a sequence, and that is the recursive method. And that's what this one looks like. Recursive sometimes is hard to understand what's going on. In a recursive, you're always going to be given at least one initial term, and then you're going to be told how to get from one term to the next term. So a sub 1 equals 3, great. I know the first term. We have to figure out the fifth term. To get there, we have to go through all of the other ones, starting with the second term. First term is 3. What is the second term? This tells us how to do it. So a sub 1 equals 3. What if I say, let's let n be equal to 1? Like in this yellow equation, if I let n be equal to 1, it would be a with the subscript of 1 plus 1, which means if n equals 1, this is reading as a sub 2, so we got right here, equals 4/3 times a sub 1. A sub 1 is 3, that's the first term. Multiply them together, and it turns out that our second term is 4. This yellow, the way you interpret it is, to find one term, you multiply 4/3 times the previous term because n comes right before n plus 1. That's what this recursive is telling us to do. To get a term, you take 4/3 times the term right in front of it. So let's go for the third term. This one will be a fraction. To find a sub 3, so now if I plug like 2 in for n, if I want to be specific here, plug 2 in for n, 2 plus 1 is 3, that's a sub 3 equals 4/3 times a sub 2. Here is a sub 2, so 4/3 times that would give us 16/3. This is saying take 4/3 times the previous term to get the next term. What then is the fourth term? 64 over 9. You multiply by 4 over 3, we get this. Last one, we want the fifth term. How about, Rebecca, what's the fifth term?
4/3 times.
Okay, so multiply by 4/3, what do you get?
Oh. 256.
Over? So times 4/3. You multiplied your numerator by 4. Multiply your denominator by 3. 27. There's our fifth term. I don't like recursive as much because I have to find all these other terms to get to the one that I want. But sometimes this is the way you see them described. So we have to interpret what they are saying. So those are sequences. Now let's take a look at some of these series problems. Directions for this one are to write this series into sigma form. It doesn't say we have to evaluate this one, so I'm not actually going to add them all up. I just want to write what would this look like if it was in a sigma form. I prefer the arithmetic. Is this one arithmetic? Are we adding the same number every time? We added 7, then we added 14, so it's not that. Are we multiplying by the same thing every time? What are we multiplying by? 2. So our common ratio is 2. Our first term is 7. I can see that by looking at this list. So can you write a formula for a sub n? If you need to, flip back to the previous page, look at that formula. How would you write this one out into the explicit form? All right, Grace, what is it going to look like?
A sub n equals 7 times 2 to the n minus 1.
Good. So first term times the ratio to the n minus 1. This is the formula. If I plug 2 in for n, I should get 14. If I plug 3 in for n, I should get 28. The problem is I don't know what term number this one is. I don't know if it's the 12th term. Is it the 20th term? Is it the 100th term? I don't know. And I could find all of these intermediate terms and get there. That might take quite a while. So we need to find another way to figure out what term number that is. Where are we going to plug this into this equation that we just found? Where does it plug in?
Could you solve for n?
Solve for n. So where does this get plugged into here then?
A sub n.
A sub n. So 14,336 equals 7 times 2 to the n minus 1. The goal is to solve this thing for n. Should we multiply 7 times 2 to call that a 14? No, definitely no. But what can you do? Step 1. Divide by 7. Good first step. Divide both sides by 7. So 14,336 divided by 7 is 2,048. And now I feel like I'm kind of stuck. I can't just divide by 2 because that would like what would happen to the right-hand side. This is an exponential problem that is kind of stuck. You have to think back to earlier in the class here. When you are stuck in exponential, what do? Log. Log base 2 of 2048 equals n minus 1. Now this is something you can put onto your calculator. You can do this, the log change of base on your calculator. So math, I'm going to scroll up to log base 2 of 2048. 11. So when you evaluate this log on the left, we get 11 equals n minus 1. So what does n equal? 12. Now, answer the question. We've done all the work. We have to put it into sigma form. So look at what we have. Put into sigma form. So the function, 7 times 2 to the n minus 1, that's what goes on the inside. N equals 1 to 12. So it's finding the sum of these first 12 terms. That's all we need to do. We don't actually have to add them. That's just what the summation would look like. Next example is already in sigma form, and it doesn't have any directions other than just this. This means find the sum. Now, one thing you could do that maybe if you want to check it is you could use the summation, plug it in there just like that, see what the number comes out to. But like I told you in some of those previous ones, know how to use the formula because there become some problems where that sigma isn't going to help you at all, and you have to understand how to use the formula. Like going back a little bit to this last problem, the summation wouldn't have helped us there. This is another one where I want you to know how to use the formula so you can solve the more difficult ones. So is this an arithmetic? No. Isn't this exactly in the form of what the geometric looks like? Specifically, what is the first term here? 2. What is the common ratio? 4/3. Scroll up a little bit. Gave this to you earlier. Here is the formula we're talking about. It is the sum of a geometric series. And it is finite. Tomorrow we'll get into the infinite. But this is the sum for a finite geometric series. We know a sub 1. We know what r is. We even can look at this summation and figure out what n is going to be equal to. So let's put it all together. The sum is equal to first term, that's a sub 1, 1 minus 2 to the, what is the n for this one? 30. It's 1 to 30, so 30 terms over 1 minus 2. This is what I want you to put into your calculator. Actually, it's not 2 for the ratio. What is the ratio? 4/3. Nick had his hand up. He's going to correct me there, weren't you? Yeah, so first term, common ratio. Know how to use your calculator. Can you enter this in and evaluate it? Looking at a big number here. The first number was 2, and then we kept multiplying it by 4/3 times 4/3 times 4/3. By the 30th time, it's going to be a pretty big number. And then we're adding them all together. That's what this sigma is doing. We're looking at a number in the 30,000s. 33,591.994. Approximately, because we had to round, but as always, we're going to round to 3 decimal places. So again, know how to use those formulas. I anticipate that this one will be provided for you, but know what it is, know how to plug it in, know how to use it, know when to use it. All right, and then this is our last one. It looks like this. It's very similar to the previous one. I look at the setup. It is geometric. It's a number times a number up to the 1/2 to the something power. It's looking just like a geometric, but there is a little difference here. Normally, what is the exponent looking like? But this one has n. Normally, what is the lower bound? This time we have 0. So that makes it look a little bit different. What is this sum going to look like? The sum is equal to, let's see what we can figure out here. The numerator is supposed to be 1 minus the ratio. What is our ratio for this one? 1/2 over 1 minus 1/2. But in the numerator, it's 1/2 to the n power. What do you think n is going to be this time? And it's not going to be 10. 11. Where's this 11 coming from? Well, if it had been 1 through 10, then we would have had 11 terms, right? But if we're going from 0 through 10, if I start counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's 11 terms. So we actually have 11 terms in this one. Then, normally we say out front it is a sub 1, like the first term. Maybe the more accurate might be the leadoff term. In this one, the leadoff term, the very premier first one that you get is if you plug 0 in for n, what's 1/2 to the 0 times the 20? So 20 is what's going to go out there. It sure looks like it from the equation. It is. It's going to be that 20. But recognize because it's 0 and 10, it's actually 11 terms that are in there. And because this is to the nth power, that's why this is a 0. If it's n minus 1, I hope that would be 1 down here. So then here's our equation. Can you put that into your calculator? You know how to put those in there. It's not necessarily an easy thing to do. Lots of small mistakes we might make with pluses or minuses or the fractions. So know how to enter that in there. We should be looking at a number slightly less than 40 here, pretty close to 40. So we want 3 decimal places. This 0 at the end is a significant digit. It's showing that we're precise to 3 decimal places. So it's about 39.980. That is the sum of that series.